Hello and welcome back. In this video, I want to discuss another way which we can calculate the electric field using something called Gauss's Law. But before I can explain what Gauss's Law is, I first need to explain what electric flux is. And basically, the idea of electric flux is a measurement of the amount of electric field that is flowing through a surface. So what exactly do I mean by that? Well, let me kind of just show a little picture here. So the idea is that I have this sort of imaginary surface that I've drawn at this black box here, and there's electric field lines that are actually passing through this surface. So the flux is a measurement of the amount of electric field that's flowing through this surface. And the idea is that the electric flux that flows through a surface depends on three things. It depends on the strength of the electric field, it depends on the area of the surface, and it also depends on how that surface is oriented with respect to the electric field. So for example, if I imagine looking down the length of the electric field, so I'm actually looking in the same direction that the electric field lines are pointing, if this plane was parallel to these electric field lines, then what I would see as I looked down the direction of the electric field lines is I would just see a sort of line. I would just see the side of this surface. Now, as I start to rotate the surface, I start to see a little bit more of this box here. And then finally, if I rotate this box so that it's completely perpendicular to these lines, then I start to see the entire box. So we can imagine that if I have electric field lines that are traveling, say, into the screen here, when the plane is parallel to this, none of these electric field lines are actually going to pass through this. If I rotate it a little bit, I'll have some of the electric field lines that will pass through it, and if the surface is now perpendicular to the electric field, all of the electric field lines now are going to pass through that surface. And so it turns out that the electric flux is just equal to this formula down here. So the electric flux is equal to the magnitude of the electric field times the surface area times cosine of this angle phi. And this angle phi is the angle between the electric field and the direction that is perpendicular to the surface. So when this surface here is perpendicular to the electric field, these two arrows here will be pointing in the same direction, and so this angle will be 0. And so basically what Gauss's law says is Gauss's law says that the flux through a closed surface is going to be equal to the charge that is enclosed in the surface divided by this constant, which is called the permittivity of vacuum. And it's related to the constant K that we talked about in Coulomb's law by this formula right here. So K is equal to 1 divided by 4 pi times the permittivity of free space. And basically what this is saying is that because electric field lines emanate from positive charges, the only way I can have electric field flowing out of a closed surface is if there is a positive charge somewhere inside that surface. Likewise, because electric field lines can only end on a negative charge, the only way I can have electric field flowing into a closed surface is if there is a negative charge enclosed inside that surface. So to understand how Gauss's law works, I want to work through a very simple example. I want to use Gauss's law to calculate the electric field that is generated by a point charge. And the reason that this is such a good example is because we already know that the magnitude of the electric field that is created by a point charge is equal to kq over r squared. So I want to show how we can arrive at this same formula using Gauss's law. So the trick to applying Gauss's law is that you always pick a surface so that the magnitude of the electric field is the same at every point on the surface, and the electric field is perpendicular to the surface everywhere. So for a point charge, I choose the Gaussian surface, that's the surface that's going to enclose the charge, as a sphere that is centered on my point charge, so that every point on the surface is the same distance from this charge. So the magnitude of the electric field will be the same everywhere on the surface. And because the electric fields point radially away from this charge, the surface is going to be perpendicular to the electric field everywhere. So what this means is that the flux through my surface is just going to be equal to the magnitude of the electric field at the surface times the area of the surface. And the area of a sphere is 4 pi r squared. So if we apply Gauss's law Gauss's law tells us that the flux through a closed surface is equal to the charge enclosed in the surface divided by the permittivity of free space. And we said that the flux was equal to the magnitude of the electric field times 4 pi r squared. So we have 4 pi r squared times the magnitude of the electric field is equal to the charge enclosed divided by the permittivity of free space. And if I solve for the magnitude of the electric field, I see that this is equal to 1 over 4 pi epsilon naught times q over r squared. And as I mentioned before, this number, 1 over 4 pi epsilon naught, is equal to k. So this is equal to kq over r squared. So we see that we do indeed get the same formula using Gauss's law. So let's go ahead and look at a more complicated example. So here I have a point charge that is placed inside a hollow conducting sphere. So this is a conducting sphere. It's made out of a metal and it's hollowed out inside. And I've placed a charge inside this. And what I want to do is I want to calculate the electric field everywhere. So I want to calculate the electric field inside this thing, inside the conductor, and then outside of this whole thing. So inside the conductor, things are very easy, right? Because if I choose a spherical surface inside here, it's going to be exactly like it was in the previous example. So we're going to see that the electric field inside here is just going to be equal to kq over r squared. And the reason that it's going to be so simple is because, remember, Gauss's law only depends on the charge that's enclosed inside the surface. So all of this metal, it's not enclosed in the surface, so it can't possibly have an effect on this calculation. And because everything is spherically symmetric about the charge, we don't have to worry about anything. We can pick this very simple Gaussian surface and do the calculation the same way that we did just before. So now what happens if we're actually inside the conductor? Well, we already know what happens when you're inside a conductor. The electric field is going to be equal to 0. So what we can do is, because we know the electric field is going to be equal to 0, Gauss's law actually tells us a little bit of something. Because Gauss's law says that the flux is going to be equal to the charge enclosed divided by epsilon naught. So if the magnitude of the electric field is 0 inside the conductor, then the charge enclosed inside the conductor has to be 0. So what this tells us is it tells us that the charge that builds up on the inside surface of this metal has to perfectly cancel the charge that was placed inside this metal cavity. So if this is some charge plus q, the charge that forms on the inner surface of the metal is going to be exactly minus q. And then of course we're going to have this positive charge that's going to build up on the outer surface of the metal. So finally, what's the electric field like on the outside? Well, again, we can just do the same thing we did before. I can pick a spherical surface that encloses this entire thing. Didn't draw that with a proper 3D perspective. It should be a dashed line back there. If I calculate the electric flux through this, again, it's going to be the same thing. So the flux is going to be equal to 4 pi r squared times the magnitude of the electric field, and this also has to be equal to the charge that's enclosed divided by epsilon naught. So I find that the magnitude of the electric field is just kq over r squared. And again, the idea is that this metal was initially neutral. It had just as much positive charge as it has a negative charge. So the only charge that's enclosed is just this charge right here. Because, again, remember, the negative charge that forms on the inside surface of this metal perfectly cancels the positive charge that forms on the outside of the metal. So all of this charge on this conducting sphere doesn't actually really matter when we do this calculation using Gauss's law. So the last thing that I want to do is I want to talk about something called a capacitor. And a capacitor is one of the two circuit elements that we'll talk about a little bit later in the year. And what a capacitor is it's two metal surfaces which are placed extremely close to each other. And when these two metal surfaces are connected to opposite ends of a battery, opposite charge will build up on those two surfaces. And so what I want to do is I want to use Gauss's law to calculate the electric field outside of these two metal plates, as well as in between the two plates. And so the first thing I want to do is I want to consider applying Gauss's law to just a very large sheet of charge. So let me kind of just draw a picture here, and I'm not very good at drawing a 3D perspective, so just kind of bear with me here. So I'm going to draw this very large plane, and let's suppose there's a whole bunch of positive charge that's placed on this plane. So let me just draw a bunch of plus signs here for positive charge. And because there's positive charge on this plane, there will be electric fields emanating from this. So I'm going to have electric fields that are coming out like this, as well as electric fields that are going to be going in the other direction. So I'm going to have an electric field going in this direction as well. And let's suppose that the charge that's distributed on this surface has a charge per unit area given by sigma. So sigma is the charge per unit area on the surface of this, this metal surface here. And so what I want to do now is I want to apply Gauss's law to this surface right here. So let me kind of draw this. I'm going to have a cylinder here, and the surface of the cylinder is going to be parallel to the surface right here. And it's going to pass through the surface. So it's going to come through here, and it's going to actually cut through the surface that's holding this charge. And it's going to pass through on the other side, and then poke out on the other side. So again, I'm not very good at drawing these 3D perspectives, but I hope you can kind of see what I've drawn here. And so the idea is that the sides of the cylinder are going to be parallel to these electric field lines. So I don't have any flux through the side surface of the cylinder. The only surfaces that'll have electric field flowing through them are these two ends of the cylinder. So this end and this end over here. So the total flux through this whole thing is just going to be equal to 2 times the area of the end of the cylinder times the magnitude of the electric field. And according to Gauss's law, this is going to be equal to the charge that's enclosed inside the cylinder. And that's just going to be equal to the charge per unit area times the area of the surface divided by epsilon naught. Okay? Now the trick to this is that if I imagine let me go ahead and just kind of extend this. So let me go ahead and take this cylinder now and extend it all the way over to the very end of the screen. Now, what Gauss's law says is that because the total charge that's enclosed in this really, really long tube, it's still the same, right? Because all of the charge that's enclosed, it's caused by this little surface right here that I'm enclosing, this part right here. And that hasn't changed at all. So what this means is that the electric flux through this surface over here is the same as it was when it was way back here. So what this tells us is that if you have a very, very large sheet of charge, the electric field is the same anywhere. So it doesn't matter how far away you get from this sheet of charge, the strength of the electric field is always the same. And you might think, well, why is that? Shouldn't the electric field get weaker the further away you get from the charge? But the reason is because this charge, we're assuming it extends infinitely in all directions. So we're assuming that this is an infinite plane of charge. So we have an infinite amount of charge, and because of that, the strength of the electric field actually never really gets weaker, even as you get further and further away from it. And this has a very big consequence, because if we imagine we have these two surfaces here, there are electric field lines that are created by this. So we've got these electric fields that are emanating from this positive charge right here. So they're going to look something like this. And likewise, I have electric fields that are created by this. So these electric field lines are going to go like this. And even over here in region 1, there's electric field lines that are caused by this surface right here. So there's going to be electric field lines that are pointing inwards towards this. And what we can see is that the electric field that is caused by this positive plate, which points to the left, is going to perfectly cancel the electric field that is created by this negative plate, which is pointing to the right. So over here, the electric field is going to equal 0 newtons per coulomb. Similarly, over here on the right side, the electric field is also going to equal 0 newtons per coulomb. And the reason that this happens is because the strength of this electric field that's created by this plate doesn't decay as we move further and further away from this plate. So even way over here, the electric field that's created by this negatively charged plate is still the same. And so it'll perfectly cancel the electric field that's created by this positively charged plate, because these arrows will be pointing in opposite directions. However, in between these two plates, these electric fields will be pointing in the same direction, because it's going to be pointing away from the positive charges and towards the negative charges. So now if I apply the Gauss's law to a cylinder, let me kind of just draw the cylinder. This will look really ugly here, but I'm going to kind of do a cylinder that looks like this. So one end of it's going to be in between the two plates, and one end is going to be outside the two plates. And now what we have is, if we apply Gauss's law to this, so we have the flux is going to be just equal to the magnitude of the electric field times the area of the surface, because the only surface that the electric field is going to be flowing through is this surface right here. There's no electric field flowing through this, so the flux through this surface right here is 0. Okay, there's no electric flux through this end because the electric field out here is going to be 0. So now if I set this equal to the charge that's enclosed, remember the charge that's enclosed, if this has a charge per unit area of sigma, then the charge that's enclosed by this is sigma times the area of this cylinder divided by epsilon naught. And so we see the areas cancel, and the electric field that's in between the two plates is just going to be equal to sigma divided by epsilon naught. If you recall before, the electric field that's caused by just a single plate was sigma divided by 2 epsilon naught. So this is just twice as much, and that's because I've got two plates that are adding together. Their electric fields are adding here in this region too, so it's just going to be twice as much. And so at this point, I think I'd like to end this video, and in the next video, we'll talk about the potential energy that is associated with this Coulomb force.